Okay, here's my solution for the problem that we did on Wednesday of week 1. So we did a problem where we had two objects that were charged with the same charge because they repel each other. And the question was, given the orientation of the setup and the mass of the objects, find the charge on each object. And you were given the M and the L and theta. Okay, so we start always by doing a free body diagram. And so I'm going to choose the ball on the right. I would get the same answer if I chose the ball on the left, of course, because of Newton's third law. But to do a free body diagram, the first step is to choose the object. So I choose the object, and then I'm going to draw all the forces on the object. So I have the force of tension going upward and gravity going downward. And now the force of gravity is m times little g. And because these are equally charged, either positive or negative, they're repelling each other, and they repel along the line connecting them. So it's actually important that both the strings are the same length, because that line connecting them is horizontal. So we'll call this F sub E for the electric force. Okay, so I'm going to choose axes here, and I'm going to choose these axes. They aren't the ones you have to choose, but those are the ones I did choose, I should say. And so the tension force has to be separated into components in the x and y direction, where this angle here is theta. And so I write down the sum of the forces in the x direction and the sum of the forces in the y direction is equal to mass times acceleration in the x direction and mass times acceleration in the y direction, and both of these are 0. So this is an equilibrium problem, static equilibrium, where the sum of the forces in all directions sums to 0. And so what we get here in the x direction is the force of tension times, let's see, this x direction piece is opposite the angle, so sine theta. And in the y direction, it's ft cosine theta. In the y direction, it's positive. In the x direction, it's negative. Plus, now we have gravity. Let's see, so gravity's in the y direction. That's mg. It's actually in the negative direction, isn't it? And the electric force is in the positive x direction, so that's k, q times q, divided by r squared. Okay, so I check now, and I note that I have too many unknowns. I'm looking to find the q, that's okay, and I can solve one of these equations for tension, but I don't know what r is. So I'll have to be careful now to rewrite r. So I note that r, this distance between the two, is equal to, let's see, L sine theta would be one of them, and so both from side to side is 2L sine theta. It's just a length. So actually I think I'm going to write that in right now. So we'll cross this out. And we'll write 2L sine theta squared. So what I do is I note that these two equations allow me to solve for the tension force. And so the force of tension using the bottom equation is equal to mg over cosine theta. And using then the top equation, I can rewrite this as negative mg cosine theta times sine theta plus k, and I'm going to simplify this now to be q squared divided by 2L sine theta squared equals 0. Okay, so that means that I need to solve for q squared. And if I solve for q squared, so let's see, I put this term on the other side, mg, and sine theta over cosine theta is tangent theta divided by k, and then multiplied by 2L sine theta squared. But now I'm going to take the square root, so it's going to look like that, and I just get q. Okay, so I think that looks good. So now, let's see, now what do? Now I'm going to plug in numbers, and so the numbers that we're given here is that m is 0.003 kilograms, and I'm going to be careful to do this in SI units here, and the L was 1 meter, G, so where G, little g, is 9.8 meters per second squared, and now we've learned that K is equal to 9 times 10 to the 9. And this is going to be an SI unit, so I can actually infer what the units for K have to be. So if I have something that looks like this, giving me a force which is newtons, then K must be newtons times meter squared divided by coulomb squared, where a coulomb is a unit of charge. Okay, so all I have to do is just plug in these numbers, so I'll pause here to plug in those numbers. Okay, I'm back, and I plugged all that into my calculator, and I got that Q is equal to 7.5 times 10 to the minus 7, and now my unit here is this coulombs. Okay, so I might want to put that in. I could leave it in engineering notation like that, scientific notation, or I could use the prefixes. So a millicoulomb is 10 to the minus 3, and a microcoulomb is 10 to the minus 6. So it's 3/4 of a microcoulomb, or, if I'm so inclined, I could write it as 750 nanocoulombs. And that's the answer. Okay.